Hello and welcome. In this video, we want to sketch graph of functions with the information of the continuity of the function. A sketch graph of a function that is defined on all real numbers and is continuous except for the stated discontinuities. The first function that we want to graph is a function that is continuous everywhere except at these points. It has a removable discontinuity at -4, and also it has infinite discontinuity at 2. So the function is continuous everywhere, but it has a removable discontinuity at -4 and infinite discontinuity at 2. Let me draw x and y axes here. Let us suppose -4 is somewhere here and 0.2 is here. The function has a removable discontinuity at -4. What was removable discontinuity? Removable discontinuity happens when we have a hole at that point. So you have to graph something, any graph works, but at -4 you have to put a hole, an empty hole. So let's say we put hole here. Whatever you want to graph in the left side of this hole is completely optional. You can graph something like this, or maybe something like this, or any other thing. But it should be continuous in the left side of -4. Attention, it's continuous everywhere except -4 and 2. So I prefer to graph this in the left side of -4. But what about the right side of -4? Again, it's completely optional and it's up to you what you want to graph in the right side of -4. Maybe you graph something like this, or a horizontal line, or any other graph. Because we have no information, you can graph anything you want. It's completely optional. I graph something like this, but we have some information about 0.2. We have to have an infinite discontinuity at 2. Infinite discontinuity means that at that point we have a vertical asymptote. So let me draw a vertical asymptote at 2. Let's say this is our vertical asymptote. And let me erase this part here. I want to graph it again. Because we want to have infinite discontinuity at 2, I am going to start from -4. But when I approach to point 2, I have to go toward positive infinity, or maybe you prefer to start from here and go to negative infinity. It's completely again optional, but you have to go to infinity because we have infinite discontinuity at 2. And going up or down is completely optional because we have no information about that. Here I prefer, for example, to choose going downward. Maybe you prefer to go upward. What about right side of 0.2? What we have to graph in the right side of 2. So you can graph anything you want here, but don't forget at 2 you have infinite discontinuity, so maybe it's better to go toward infinity when you approach to 2. So maybe something like this is a good idea, or maybe you prefer to draw something like this and go to negative infinity. Again, it's completely optional. You can draw any curve you want here, but you have to approach to positive or negative infinity. I prefer to keep this one. So this is one answer for this question. We have a removable discontinuity at -4 and an infinite discontinuity at 2. Let me add something about -4. At point -4, I put a hole because we want to have a removable discontinuity. But attention, you can give a value to your function at -4. You can put a point for -4 somewhere above -4, below -4, or on the x-axis, something like this. You can put a point here maybe, or any other point, maybe here or here. It doesn't change anything, but it's not necessary to give a value to your function, to define your function at -4, because removable discontinuity only means that we have a hole at that point. But don't forget, you should not put these points here and fill that hole. No. If you fill that point, then the function is continuous at that point. You have to leave it empty. It's completely optional again to give a value at -4 or leave the graph as this. The next question is, we want to have a graph that has a jump discontinuity at -4 again, a removable at 0, and finally infinite discontinuity at 2. Based on this information, we want to graph our function. I highly recommend you to pause the video right now and try it by yourself. And attention, your answer should not be necessarily similar to mine, because we can graph different things with this information. But the generality of your graph should be the same. You have to follow these rules that we have for function. Jump discontinuity at -4, removable at 0, and infinite discontinuity at 2. So in this question, the important points for us are -4, 0, and 2. At -4, we have a jump discontinuity. What it means that we have a jump discontinuity. Jump discontinuity happens when the right limit and the left limit exist, but they are not equal to each other. So jump happens at that point. To graph such function, I am choosing my jump from here to here. Maybe you choose 2 different points, 2 different holes. And I want to, for the left side, connect my graph to this hole like this, and for the right I use this one. And attention, you can fill one of these holes and it doesn't change the discontinuity. Discontinuity means that from the left and from the right we approach to different values. Here, if we approach from the left to -4, we get to here. If we approach to -4 from the right, we get to this value. So as you can see, the limit does not exist, and this means that we have a jump discontinuity. We have to have a removable discontinuity at 0. Removable, if you remember from the previous question, means that we have a hole, but from 2 sides, from the left and from the right, the function is connected to that hole. It's not like a jump discontinuity. So let me, for example, continue this curve and bring it here, then I put a hole here, and then I continue from here. At 2 we have an infinite discontinuity, so we need asymptote here, and then you can decide to go up or down. Here I prefer to go up. What about right side of point 2? Any graph works, something like this, but don't forget it's better to draw a function like this that shows that the function approaches its asymptote. So this graph has all of these properties, but attention again, you can answer completely different way this question. Maybe you put these holes here and here. Because we have more information, we cannot graph exact answer. Let's do one more question like this. We want to graph a continuous function that is continuous everywhere, but it has discontinuity at, for example, 0 and 4. But we have some more information. But we know that the function is continuous at 4 from the right and continuous at 0 from the left. So we have discontinuity at 0 and 4, but at 4 the function is continuous from the right, and at 0 is continuous from the left. So based on this information, we want to graph our function. Let me again draw x and y axis. The problem is at 0 and at 4. 1, 2, 3, 4. Let's start with point 4. We have to have a discontinuity at 4, but we have to graph something that shows continuity from right. Continuity from right means that at 4 you don't have an infinite discontinuity, or actually we are connected from right to the value of the function. Let's say at point 4 the value of the function is somewhere here. Then you have to connect your graph from the right to 4. Why? Because look at this, the function is continuous from the right at 4. So if it is continuous from the right, so then it should be discontinuous at 4 from the left. So when we approach 4 from the left, we have not to get to same value. Otherwise, if we connect something like this, then the function is completely continuous. But we want to graph something that shows discontinuity at 4. How we can achieve something like this? When we approach 4 from the left, we have to get to another value. Let's say we put the value here at the negative values. So when we approach 4 from the left, we approach to here. But is this the solution? No. Don't forget we have some problem at 0 as well. But this shows the idea. So when we approach 4 from the left, we should not get to here. I deleted the graph. Let me draw it again here. But from the left, we can get to this hole. As you can see, what happens here? From the right, the function is continuous, because from the right, the function approaches its value. The value of the function is here. It's filled. But from the left, it approaches to a hole which shows discontinuity from the left. At 0, we have opposite situation. At 0, we want continuity from left, but discontinuity from the right. So I'm going to put a hole on the y-axis. Let's say we put it here. Then I'm going to connect it to that hole. Let me draw this part again. So something like this. But from the left, we want a function that is continuous at 0. So let me put a field point at the y-axis somewhere here. Because we want the function to be continuous from the left at 0, I'm going to graph something like this. This graph has these properties. Let's review. At 0, the function is continuous from the left. This graph satisfies that condition. From the left, when we approach to 0, we approach to the value. But from the right, when we approach to 0, we approach to a hole. So from the right, the function is not continuous at 0. At 4, we have opposite situation. I hope you like this video. If you like this video, please subscribe in my channel and see you in the next videos.